We're going to talk about section 10.5, separation of variables and heat conduction in a rod. So do heat conduction. And when we talk about a rod, we're talking about a solid cylinder. So with this solid cylinder, it's going to be insulated on the sides. So no heat is going to pass through the rod. So we don't have to worry about the surrounding temperature, the air temperature, or heat escaping from the rod or heat coming into the rod. We only have to worry about this closed system that we have established. So we're going to heat it up, but then we get to control how the heat is going through. The ends are going to be 0 degrees. And L is going to be length. So we're going to have U of X and T is going to give us the temperature. So X will be the distance along the rod where we're at with 0 on one end and L on the other. And then T is going to be time. So depending on where you're at and how long has elapsed, that's going to tell you the temperature of a specific spot on the rod. F of X is going to be the initial temperature. Now it's a function here because we might have a different temperature at different spots on the rod. And then we're also going to have something called the thermal diffusivity. It's a constant that's going to be for any given material. And that is going to be alpha squared. And so this alpha squared is going to be K over rho times S. K is the thermal conductivity of the object, rho is the density, and S is the specific heat. So it's how we can establish that. And now what's going to happen is we have our rod. Over here is where X equals 0. Over here is where X equals L. And then our rod is L units long. So we're going to use this equation, alpha squared, the second derivative of U with respect to X. And that should be a partial derivative there for both of those. Is equal to the partial derivative of U for T. So written another way, a little bit of shorthand, we can write it that way. And now with our given information that the ends are 0 degrees, our temperature at 0, and no matter what time, is going to be the same as the temperature at our L, no matter what time, is going to be equal to 0. And U of X at 0 time is going to be our F of X, which will be our initial condition, with our X's being from 0 up to L. Whoops, that L should be included. And so what we're going to do is we're going to see this with a graph of our T versus X. And we're going to go from 0 up to our L. And over here, we have our u of L and T equals 0. Over here, we have our u of 0 t, which also equals 0. And then here in the middle, we'll have what we're looking at with our whole u of xt. And this bottom edge is going to be our u of x0, which is our f of x. So this bottom part is our initial condition, and our u's here on the sides are both the boundary conditions. And so we're going to use all that information to then find out what's going on here in that middle part. So with our equation, we can use separation of variables. Now, in order to do so, initial equation is that. Now we want to assume that our u of x and t is equal to some function only of x's times some function of only t's. So if we can do that, we can rewrite the equation. And then we can keep on going further. And this can equal some mu value. That's going to be called our separation constant. Because that's the constant we get after we've done our separation. So looking at this portion, let's clear the screen. We have this. Well, we can multiply our t over and then subtract, and we get a first order. Now we can make our characteristic equation. And minus. So R equals mu. So then our t is going to be something times E mu t. Now, on the other end, we can look at only the x's. And then multiplying and moving things over. And then our characteristic equation. And then solving for R, we end up with plus or minus square root of mu over alpha. And I'll make that minus look more like minus. So now, depending on what our mu is, we can do a couple of different things. And this is kind of like what we did before with the lambda. You have different situations and you're finding your different characteristic equations and so on. So if our mu equals 0, then our equation simplifies to there. where this X is a capital X and this X is a lowercase x. And now we can use our initial conditions, or excuse me, the boundary conditions, to find out what our C1 and C2 are. Cu of 0t equals 0. But that's going to be the same as x of 0. Same thing with our u of lt being 0. That was x of l. So with these given conditions, and you can plug them in, our capital X equation, capital X of x, is just 0. So that's going to be rather uneventful. Everything just stays at 0. If our mu is positive, then our r is plus or minus square root of mu over alpha. And our x equation that one's minus. Again, do your initial conditions. So we'll plug in a 0, see what happens. Plug in an L, see what happens. And it actually turns out our x equals 0 again. So again, fairly uninteresting. What happens when mu is negative? So in this case, our r is going to be plus or minus I square root absolute value of mu, because now we want to avoid the negative under the square root. And so our x equation is a C1 sine of square root of absolute value of mu over alpha times t plus C2 cosine of that same thing. And whenever we solve through things, we're going to get down to knowing that our C1 is going to be, or sorry, C2 equals 0. And now our C, we're going to have the C1 times sine of this. Oops, that should be L. Just erase. There we go. Equals 0. So either that is 0 or that is 0. So if the C1 is 0, then everything just equals 0 again. Uninteresting. But if our sine portion is 0, that's going to let us find which mu values are going to work. So in this case, if mu is negative alpha n pi over L squared. We know it's got to be negative, so that's why we throw the negative in there. So if we plug this in and solve for our equation, it's going to be some value. Now, we don't know what the C2 is because, or excuse me, our C1. Because we established that our sine was 0. We don't know what C1 is. So there's potential for it to be whatever based on our initial conditions. And then we just have to look at our mu. And if we plug our mu into this, you plug that in, it's going to simplify to this. Where our n is going to be a 1, 2, 3, positive whole numbers going along. So now we established earlier that our u, and we're going to use our u for specific n values here, was our t times our x. So that was our assumption back in the beginning about making it separable. Where did I put that? There we go. So when we go to the end, it's going to be our x times our t. So our t value is this, but we now know what our mu is, so we can change that. Times our x. And n being 1, 2, 3, and so on. Oops, there's a C1 in front too. So, but now we have these two different constants, so we can just combine those together. And it'll vary depending on what n value we pick. And so that's for whatever n values we're using. We're using all of these n's. So our overall u is going to be a summation of these. And now to find these k values, this should look kind of familiar. Our Fourier series, that we can use our boundary conditions to make your t a 0, then this whole thing is going to disappear. And of course, this will work for all the x's between 0 and L. But this, since it's exactly a sine Fourier series, we can then find our k's. There we have it. Whoops, hit the wrong button. There we go. And of course, in this case, this f of x was the u at x 0. So that our t did not matter. And if that u is going to be an odd function, since sine is odd, two odds multiplied are going to give you an even. We then simplify a little bit further to get that. So you can see how we can do a real life example in real life situations where we're using all this Fourier series stuff and having it solve equations and actually do real things.